We start with chapter 3. We're going to start looking at how students build number sense. Now that we've played with numbers, talked about what numbers are and how students view numbers, we start to look at the operations and properties that are involved with numbers. So we begin chapter 3 um, here with an outline or picture of our textbook here. So I always want to remind you when we do our notes, always have that textbook open because it definitely has more information than within the guided note sheets that we provide. So you'll see these student learning objectives around mental computation, thinking about whole numbers, addition, subtraction, and so forth, all the way back down to where we end with orders of operation, where students have to, we have some common agreement about the order that we do our calculations. Otherwise, how would we all know how to get a similar answer, right? And then also exponents, with the role of exponents play. So that's what we're looking at. Let's go ahead and look at the notes here. So we start with addition and subtraction. And I really do want you to start with think about and discuss. If we were in class, we would play these videos, but I really do want you to view those and really look at the amazing thinking that is going on within the context of these two students. You have these two students who do it, and they solve the problem 90 minus something equals 75. So some amazing thinking goes on within that context. So take a few minutes to do that. They're short videos. And then really imagine what is the type of feedback you would give, right, these students, especially Rocco in this one, and how he decides to solve it. And so, again, just to give you a heads up on that, Rocco solves that problem. The problem is 90 minus 75. He does something like this, and I just want to introduce it to you so that you have some motivation maybe to click on that one. He solves it where he does 100 minus 75. That's what he does first. And it's 25, and then he knows that 90 is 10 less, so then he just assumes the answer is 15, which it is. So, but just interesting to think about. So what is addition, right? So that's what we're thinking about. You think, well, I know what addition are. Well, I want to introduce you to addition from what we call the set theory perspective. We just study sets, and so we want to connect this idea. Remember, mathematics is about ideas. It's about language, right? We use math to describe the world in some way. And the sets, remember, were the initial way that students begin to think about things mathematically by grouping, organizing, counting, right? And so we had those set operations that we were thinking, why do we don't teach those to our elementary school students, the set operation like unions and intersections, right? But it's a perfect kind of pathway into this idea of learning about operations, that they work in some way on things. And in this case, the set theory addition of whole numbers, we can see that it's connected to the union, meaning that if you have two sets, and then we have this representation, right, the number of elements, right, n of a means the number of elements in a. We want to measure its cardinality, right? We've talked about that before. So what is a plus b? A plus B would be the number of elements in the union of those two. So the union is kind of like addition, and we had thought about that before, right? Union is a binary operation, meaning it joins two sets. Addition, right, is a binary operation that counts the number of elements in those two sets when you put those two sets together. And I know it's overkill a little bit. You're thinking, I'm not going to do addition this way. And you're not, but you can see here, in the first example, how do we show 3 plus 2? Well, it's the union of two sets with elements of 3 and 2. And so that's the way we would show it. Similar to 0, right? There's no elements, the null set, empty set. So the union would still be the 4 elements there. So interesting to think about it from a set theory perspective. We also have a measurement model perspective, which is, again, represent on a number line, which will be the next level when students start to think. We use it as a way for students to see numbers and now to see addition. So using kind of that arrow drawing, as you can see there, that's where we would mean by a measurement model. These directed areas arrows tell us kind of whether adding, and later we'll see whether we are subtracting. So again, um, that's our view of addition, and of course, introduction to chapter 3. Let's continue our work with addition and subtraction. So let's focus on properties of addition. So once we now have an idea that we have a reason to add things together, like we're going to join groups or sets, right? And you can imagine in the history of our world and civilizations of when people wanted to join things, and then they wanted to quantify this combination of things, how much, right? That's addition. Once we start playing with numbers that way, and students will play because that's what you're going to ask students to do, play with numbers, these properties emerge, or questions they would want to know. Does A plus B equal B plus A? Can I change the order how I add groups together? Right. I really want you to think about that. Right. Change the order of how we add things. It's not natural for a student to think, is it the same answer? Right. I mean, it is natural for them to think about it, but not to know that they are equal. And that's the associative property. The other one is the commutative property. And then even the idea of zero, right? That's taken a long time for many civilizations to discover a need for zero, that we want to represent nothing with something, right? And that zero is a way to, is a number, right? So we have that idea here that A plus zero equals A, or zero plus, zero plus A equals A. It's always true. It's called the identity property. Identity, maybe kind of identical is the way that comes to it. Maybe think about discuss, right? What is 7 plus 2? The second question, what is 2 plus 7, right? Think about, again, how a child would solve those problems. But notice, again, just think about the difficulty of those two problems. Not until they learn what? Once they learn the commutative property, they don't have to think about it. They solve one and realize the other one is the other solution. So again, something to think about as students learn, right? And it depends on their age when they kind of discover that commutative property. Here's another one to think about mathematics flexibly, as we've been thinking about in class, like with number talks or counting collections, kind of how we count, right? And naturally, you start to apply some of the rules, even if you don't know the rules, what the rules are. So what you see here is the same problem, but the order just changed, right? Adding together, like in some, this one 80 plus 50, 130 plus 4 and 6, there's your 140 plus 73. Over here, we could go the other way around. We could add these two together first, get an answer, and then add those two there, right? So the sums are the same for each, but again, how we put them together could be different. And which one's easier to solve, right? This would be what we call thinking strategies. I think maybe the left one, but again, it depends on how people see the problem. So we call these thinking strategies, which we're going to continue to work on in the class, right? We want you to really think that math is more about thinking, not just about doing computations all the time. So looking at these strategy here, you can see various different ways to go about solving them. So just pause and take a look at how some of these were done when we look at 9 plus 7. You already know it's 16, but younger students need to come up with strategies, and they may come up with something like this. And this goes back to those videos that I showed you earlier, and those subtraction ones, or the ones I want you to take a look at. So just different ways to do that. How are they? This is just one way that I've displayed here. And then, of course, in class, we will be working together and then hopefully coming up with a lot more ways to do these problems. Like on this one here, you can pause. Well, how do you do it? And then immediately to me, oops, wrong color, but I'll just keep it, I guess. 70. Oh, it's way too thick. I ended up with, I would have done, 70. I do that in my head first, 70 plus 40. and then I do the 2 plus 3, right? And so I get 110 plus there, so I get my 115 by the end. That's what I would get on that one, right? 115. So just something to think about. And again, our focus on understanding. Here are the answers for 3.1.2, commutative, associative. And again, I think the subtle one is, again, the moving of, which one was it looking at? This one here is a little bit, again, but again, it's not about really just the names of it. It's about the idea of the flexibility of what we could do with each of these. Oh, this one could be a little difficult to see. So you're moving the entire group here. This entire thing has been moved, right? The order has been changed, right? So that's why that's commutative, even though it looks like associative in some way. So just keep that in mind. And lastly, to end this section, part 2 here, I want to talk about the closure property. I know it seems sometimes a high-level idea that does appear in high-level mathematics, but we can simplify it. The sum of any two whole numbers is a whole number. That's it. Makes sense. Now, again, you have to put in context of there's other types of numbers, and so just because you add two numbers doesn't mean it's always a whole. Well, two whole numbers, yes, right? What if you subtract two whole numbers? Do you always get a whole number, right? Those types of things students are curious to. Is it always? Does the operation do anything fundamentally to the numbers? So it's called the closure property, and these leads us to a question where you have to play with sets, and then also thinking about um, the addition part, right? So a set is closed under addition if the sum of any two elements in the set produces a unique element in the same set. So when you add two numbers in the set, the answer has to be in the set. If it is, it's closed. If it's not closed. Is the set 1, 2, 1, 2, 3, 4, 5 closed? The answer is no, because here's the counter example. 4 plus 5 equals 9. So 9 is not an element of the original set, so it's not closed. Is 4 closed? No. 4 plus 4 is 8. 8 is not an element. Multiples of 5 are closed? The answer is yes, because anytime you add those two together, you will get a multiple of 5. So something to think about. We use the terms closed and not closed. It's natural to think about open sets, and that's a whole other discussion in mathematics. So that's why notice we're not using the word open. So again, for another level, but if you're being curious, we could talk about sets being open also. Just in this case, we're saying closed, not closed.